Alright guys, so your partner quizzes from yesterday were excellent. We did very, very well in here. The scores have been posted on PowerSchool if you want to go and check out and see how you did. I still have like 1 or 2 people that need to take it though, not from this class but from other ones. Anything from the, or for the office today? I think we're good. Thank you.
Have a great day.
You too. Happy Friday. So I still have a few people that need to take it. Once they take it, I'll pass them back with the answer keys so you guys can see how you did. Okay, but the score is on PowerSchool if you want to check that out. Okay? In the meantime, we're going to pick up with our next section on page 61. We're going to be looking at domain and range a little bit more in depth in this section. We've been hinting or dealing with that a little bit up to this point, but not really so much focusing on it. So we're going to take a look at that further in here. Up to this point, what would you classify or describe domain to be? What's your understanding of that word? Either graphically or algebraically, anything like that, yeah. The x values. Okay, so the domain is the set of x values. Okay, like all x values that work. The set of x values specifically that also have a y value. Meaning if you were to plug in an x into equation, you would get a y value or number out. Graphically speaking, you'd have a closed point at that location. Okay, so domain is if you were to plug in that x, you would get out a y. Okay, what about range, on the other hand? Yeah. There you go. It's kind of the reverse statement. Okay, this time we have the set of y values that also have an x value. So if you were to plug in a y into the equation and solve for x, you would get an answer out. So in the short case, domain are x's, ranges are y's. And we've been practicing graphically, and we're going to do that a little bit more today, but we're going to amp it up because some of these graphs have a lot of different characteristics going on with them. Some of them can be pretty simple, like the first one, and then other ones can get kind of involved, like the last one. So what we're going to do is the same process we've kind of been doing in terms of a graph. We're going to drag our pencil left and right to see where we are touching a graph, where there is a point. Okay, that would be domain. And then if we drag low to high, those are representing some range values. So if you were to start on the left and start to drag your pencil, where's kind of the first point that this graph begins? Can we find that? Yeah. -4. Can we include -4? No. Okay. So we're going to use a parenthesis. As you drag your pencil, when do you stop touching a point on your graph? In other words, where is there no more point or points located? Where are we going to end? Yeah. 2.5. Say it again. 2.5. 2.5. Somewhere right here. Okay, so if there was a closed or open circle there, we would end there. But do you notice how there's an arrow? A little tricky. So this arrow is actually going to keep going down and to the right, something like that. Were you going in terms of the range, it would be -infinity. But if we're going left to right, this is going to keep going to the right towards positive infinity. I know the arrow is going down, so you're thinking -infinity, but that's in terms of a range. Okay, range is low to high or down to up. Okay, so speaking of range, let's do that. Keeping in mind we have that arrow, the lowest the graph would go would be -infinity. It's going to go down forever. And as we keep dragging our pencil up, when do we stop touching a piece of the graph? Go, Rebecca? It would be at 5, okay? And we have an open circle, so we cannot count that. We have a parenthesis. Okay? All right, so left to right for domain, low to high for range. Let's go ahead and try our next one. Start on the left. Be careful with arrows. What's the furthest left that graph would begin? Yeah. Negative infinity, and you'll never ever reach negative infinity, so it's a parenthesis. And as we keep dragging our pencil, when do we hit, bless you, when do we hit a spot that no longer has a point on the graph? Yeah. 1. We have that open circle. But do you notice how we have more graph? So we're going to need that union U, and we're going to continue starting at that 1 value again. We're kind of skipping over 1. We're not including it. And then how far right would the graph go if we keep dragging the pencil? Yeah. Positive infinity. Good. All right. Let's try low to high. Be careful with arrows. What's the lowest that graph would go? Yeah. Negative infinity. Okay. And as you keep dragging your pencil up, when do you stop touching your graph completely? Yeah. Okay, so if I were to drag my pencil at 1, you are not touching it here, but you are touching it there. Okay? The range is tricky because maybe you're not touching it somewhere, but you are somewhere else. So we can still drag our pencil. 1 is still considered a part of the range because notice how you have a closed point there. Even though that one's open, you still have a closed point. If we keep dragging, what's the highest the graph would go? Yeah. How'd you know positive infinity? There's that arrow. This arrow is going to continue forever upwards. So positive infinity. Do you guys think you can try the next one? Start on the left, drag to the right, and then go low to high. Any takers? Go ahead, Marie.
I got negative infinity, positive infinity, because although there are open circles, there's a closed one.
Exactly. All right, so if you start left to right, we have an arrow pointing to the left, so it's going to go forever to the left. And as we keep dragging our pencil, there's something happening at 1, okay, but notice how at that point or at that location, you have a closed circle, which means you are still touching a piece of this graph. So you can keep dragging your pencil. We have another arrow pointing to the right, so it's just going to go to the right forever. So you can include any x value you want, forever to the left, forever to the right, and you'll always get a point out, a y value out. Really good. What about the range? You want to keep going? Yeah. -3 to infinity. All right, so low to high. Looks like the lowest point is -3, and it's an open circle, so we cannot include it. And notice how both arrows, if you were to extend them, would go up forever. So you are always touching a piece of the graph no matter how far you travel up. So you're going towards positive infinity. How'd we do? Pretty good? Do you guys feel like you can tackle the next 3? We're amping it up a bit. Go ahead and see how you do. All right, anybody for the number 4, first one on the left side? Go ahead, yeah.
I got negative 15 to negative 1 parentheses.
Negative infinity to negative 1, okay.
And I had a unit.
Okay.
And then I had negative 1 to 5.
All right, let's check it out. So arrow to the left, you're going to go forever to the left. As you drag your pencil, bless you, something's happening at negative 1, and there's no closed circle at that spot, meaning there's no graph. You're not touching anything. So we have to end there. So that's one interval, but we have more graphs, so we need a union. We're going to pick right back up at that negative 1. We're just skipping over it. And then as we keep dragging our pencil, looks like we end at 5 with another open circle, so parenthesis. How'd you do? Good? All right, let's check out range. Low to high, trace your graph. What's the lowest it goes? What's the highest it goes? Are there any points that we got to skip over? Go ahead, Marie.
I had negative infinity
Okay.
to 3 to 5.
3.5, okay. Parenthesis or bracket? Parenthesis. All right, so at first glance, with the way this graph looks, if you were to drag your pencil, some of you may have thought it starts at negative 3, okay? But we got to be careful because there is an arrow. This one's going to go forever down. So you technically could go all the way towards negative infinity. As you drag your pencil up, there are some open circles that can be a little confusing or tricky. At negative 1, you have an open circle, but you're still touching there. At positive 1, you have an open circle, but you would be touching over here. And it isn't until we get to about 3.5 where we have an open circle, but no other graph to touch. So we're going to stop at that 3.5. How do we do on the range for 4? Good job. All right. What about 5? Any takers? Maria, I'm going to give you a break for a second. Go ahead, Rebecca.
For the domain, I put in parentheses negative 5, infinity,
Okay.
close parentheses, and then for the range, I put in another set of parentheses, negative 3 and 4.
-3 to 4. Parentheses on both?
Yep.
All right, let's check it out. So trace the graph left to right. There's no arrow on the left-hand side, so we do have some beginning point. It's not going to be...
Oh, for range, it should be infinity, positive infinity.
For the end one?
Yeah.
Okay, I'll change that. All right, let's check out domain. So as you go left to right, we're going to start at negative 5, but we have an open circle, so it's a parenthesis. As you keep dragging, something's happening at negative 1, but we do have a closed circle, so the graph is there. We're just going to keep dragging, and arrow on the right-hand side is going to go forever to the right, so positive infinity. That one looks good. If we check out the range, dragging our pencil, looks like we start at negative 3. Can we touch negative 3? If you wanted to, could you put a closed dot there? Yes, okay, so I like the negative 3, but this needs to be a bracket because we can touch it. As you keep dragging your pencil, we encounter an open circle, but you're still touching a graph over here. If you keep dragging, we have another open circle, but you're still touching a graph over here. If you keep dragging, it looks like it stops at 4, but again, that arrow is going to continue forever up. So we can go towards positive infinity. How do we do on 5? Awesome. All right, the last one. This is good. Any brave soul? Yeah, Tori?
So I have parentheses, negative infinity,
Okay.
4, parentheses, and then 4 to infinity, close parentheses.
Okay.
And then for range, I have parentheses, negative infinity to infinity.
All right, let's check it out. So it might be a little hard to see, but we do have an arrow on the left-hand side, and there is one on the right-hand side. Okay. So starting left to right, if we have an arrow, we're going to go forever to the left. We drag our pencil. Something's happening at -1, but we do have a closed circle, meaning we can touch it. So we're going to keep dragging our graph, or pencil rather, on the graph. Something's happening at 2. Do we know what this is called? Dotted line? Vertical line? Yeah. It's a vertical asymptote. Okay, so if you take, I know it's a little tiny, but if you take a good look at this graph, the left-hand side is going down forever. Okay? You're getting close to that asymptote, but you're never touching it. You never cross it. Sometimes I reference Lord of the Rings, like I think it was Gandalf. Thou shalt not pass, right? You will never pass a vertical asymptote. Okay? So you're never going to pass it on the left-hand side, you're never going to pass it on the right-hand side, which means at this location there is no point. There is no graph. Okay? So I like this, but as we drag, we encounter no point at 2. So we're going to change that first 4 to a 2, which might change the rest of it. Okay? So we had -infinity, and we were able to drag all the way to +2. We still have more graph, so we need a union. We're just going to skip over that vertical asymptote of 2. And as we continue to trace, looks like we encounter that open circle at 4, which Tori had before, and we cannot include it. But again, we still have more graph, so we're going to skip over that 4, and arrow on the right-hand side goes towards +infinity. Okay, so we actually had 3 domain intervals for this one. We had to skip over the asymptote, and we had to skip over that open circle hole. If we check out the range, these 2 arrows are pointing down, so we're going to go forever down towards -infinity. As we keep dragging the pencil up, we do encounter a hole, open circle, but we are still touching the graph on the left. As we keep dragging, we encounter another open circle, but we're still touching the graph on the left. And with the arrow on the right-hand side going to go up forever, we can end at +infinity. That one was thoroughly involved. Did we get pieces of that? Parts of it? That's really good. Perfect. Okay, so notice how some of these graphs are pretty simple, like our first one. Other ones can get a little bit more tricky, okay? But all of these are considered piecewise functions. Notice how, or maybe not this one because that's cubic, but notice how in the other ones we had a square root, a parabola, we had 2 different lines, we have an absolute value, okay? We have different types of graphs all on the same picture. We're not always going to be dealing with piecewise functions. Sometimes we'll just be dealing with a singular equation or a singular graph. So here are some common types of functions that hopefully we're already familiar with. One of them is the constant function, like f of x equals a number, like y equals 4, y equals 5, something like that. If you were to graph a constant function, what would it look like? Can you describe the shape of the graph? Yeah. Straight line this way or this way? Horizontal, yep. Okay, so we have a horizontal straight line. What if we were to graph a linear function? mx plus b, ax plus b, whatever letters you want to use. Hopefully we know it's going to look something like that. What about an absolute value graph? What shape does that have? Yeah. A V shape. Okay, so we'll just draw a generic V-shaped graph. And then what about quadratic? Power of 2? Yeah. A parabola, square root. Yep, so generic U-shaped graph. So these are 4 common ones that you guys are clearly already familiar with. If we were to find the domains of these, okay, tracing our graph left to right, what would the domains be? Yeah. they're all going to be the same, negative infinity to positive infinity. Meaning you can pick any x value you want, and if you were to plug it in, you would always get out a y value. Whenever you have the interval negative infinity to positive infinity, it's commonly referred to as all real numbers. Have you guys heard that before? Okay. Do you know what the symbol is for all real numbers? Yeah? Yes. Okay, so it's a double-stemmed R. So whenever you encounter an interval like negative infinity to positive infinity, if you wanted to use the double-stemmed R instead of the infinities, that's okay as well. For instance, on our last graph over here, the range was negative infinity to positive infinity. If you just wanted to write the double-stemmed R, that would have been fine as well. Okay, so all of these are all real numbers. You can pick any x value and you would get out a y value. Those are nice simple ones. Okay? What we're going to do though, because those are essentially too easy for us, right? We're going to go ahead and check out some other types of functions that don't necessarily have a domain of all real numbers. Okay, where things get a little tricky. So our first one here is a fraction. Our second one is a square root, and then we even have a cube root. We're going to pay close attention to these. Can we go ahead and find the domain of these different graphs? For this fraction equation, if you were to trace left to right, what's the furthest left we would go? Do we have any places we need to skip over? What do you think? Yeah.
Would be negative infinity to negative 2.
Okay.
And then we would have a unit.
Okay.
And then negative 2.
Okay, so we start at negative infinity. As we drag, we encounter that vertical asymptote at negative 2 that we kind of have to skip over because there's no point there. We got to stop at 2 because there's that open circle, but we still have more graph, so another union, and we would have 2 to infinity because of the arrow. Okay, another kind of 3-sectioned domain piece there. What about the domain for a square root? Or particularly this square root. If you were to drag left to right, furthest left we go is negative infinity because of that arrow. And as we keep dragging, looks like we stop at 5. There isn't a big closed circle there, but if you wanted to put one there, you could. So we would need a bracket because there's a point at that spot. What about the domain for this cube root? Yeah. Yep, okay, so this one happens to be negative infinity to positive infinity. We're going to see some cube roots that are not that domain, or you could have that double-stemmed R, whatever you want to say. So what we're going to do, based off those 3 graphs at the top, those are good pictures to have. We're going to analyze a few function values in the chart at the bottom to actually determine are they a part of the domain or are they not. We already know what numbers are in the domain because we labeled them. Let's go ahead and see if the math actually checks out. Do we know what a fraction equation is called? Like, you know how a parabola is a quadratic function? Do you know what a fraction equation is called? Probably not. Have we heard rational? Maybe? Okay. So a fraction equation is a rational function. Okay. So look at the first column. Find the indicated function value. If this negative 2 is representing an x value, let's go ahead and plug it in and see what we get out. Let's see, we'll have 4 minus 2, which is 2, minus 6 is negative 4, and 4 minus 4 on the bottom would be 0. What's negative 4 divided by 0? Yeah. Undefined. You cannot divide by 0. Good. Okay. Let's go ahead and try -1 as an x value. So we'll plug it into the same equation, see what we get out. Let's see, 1 minus 1 is 0, minus 6 is a -6. 1 minus 4, we got -3. So it looks like we end up with 2. Okay, so based off of these two function values, what conclusions can you make about the domain of the function based on these computations? Remember, domains are x values that if you were to plug them in, you would get out a y value. What conclusions can you make? Yeah. -2, okay, that x value is not a part of the domain because notice how we did not get a y value out. So that means -1 is a part of the domain since we did get a value out. And notice how that makes sense based on the interval we had here. Didn't we say -2, we kind of had to skip over that because we have those brackets, you cannot count that point. But notice how -1 is within this middle interval that you identified, right? -1's between -2 and +2. So this is not a part of the domain, whereas this one is. So we'll say x equals -2 is not part of the domain, but x equals -1 is. Graphically speaking, we can see that. But notice how if we didn't have the graph, we could still reach that same conclusion because of the y values that we did or did not get out. Okay, let's go ahead and try our square root. If we were to plug in -4, we'd have the square root of 9, which is 3. If we plug in 9, we'll have the square root of -4, which is, I'll take two things here, yeah. It's imaginary, okay, so if you were to write the imaginary answer, the square root of 4 is 2, but since it's imaginary, you would need that I. So if you wanted to write the imaginary number, that's completely okay. But if you actually tried to type in the square root of -4 on your calculator, it would come up as an error message, meaning that this is kind of undefined as well. There's no real answer or number that you're going to get out. Okay, so I'd take either one of those. So based off of those computations, can we determine whether -4 or 9 is in the domain? Bless you, bless you. Go for 3. Not today.
I did like 5 the other day, and I was like, I need a video of this to show you.
Let's see, what conclusion can we make? Good, Hannah?
X equals -4 is part of the domain, and x equals 9 isn't.
All right, x equals 4 is part of the domain because notice how we got a y value out, but x equals 9 is not. Okay, we did not get a real number, a real y value out. And based on the graph above, you said that we can include any x value we want as long as it's between -infinity and 5, including 5. Notice how -4 falls within that interval, but 9 does not. So it makes sense that 9 is not a part of it. Okay, it helps that we have the graph, but again, if we didn't, you could still get the same conclusion. All right, let's go ahead and check out the last one. If we were to plug in -11, we would have the cubed root of -8. What number times itself 3 times would give you -8? Yeah.
2 No, -2.
Just -2, right? That's okay. -2 times -2 times -2 would give you that -8. Let's go ahead and try to plug in 5. This time it's just the cubed root of 8. So instead of negative 2, we would have positive 2. 2 times 2 times 2 is 8. So what conclusions can we make? Yeah. X equals negative 2, positive 2 are a part of the domain. Okay. And if we reference the graph, because we have that to our disposal, we said that every single X value you wanted to plug in would give you a Y value out. Okay, all real numbers. Notice how that makes sense, because we picked anything we wanted, in this case negative 11 and 5, and we still got a number out. Are we doing okay? Yes?
I think you meant to write negative 11 and 5.
Oh, instead of the 2's. I'm sorry. Yes, because we're talking about X values. Negative 11 and 5. Thank you. Good catch. We hanging in there? Okay. Tori wanted a 3/4 today, so we're going to stop. Okay? We'll save the next page for next week. All right? But in the meantime, we're going to have a homework quiz. Oh, come on. Where are the smiles? Yes.